Good morning. Last session we introduced the concept, a new section, and the concept of an analysis of variance. We call it ANOVA. Chapter 12 focuses on the simplest of the ANOVAs, the one-way analysis of variance, where we have one factor, one dependent variable. We said that this is an extension of the two independent sample t-test, where we are actually looking for significant mean difference across three or more groups. We compute this F statistic, which we call an omnibus F, and we said that if we get a significant omnibus F, it's telling us we have overall significance. So this F that we compute, this Fisher's F, is an overall indicator of significance. We also said that if we reject the null, we have another step, and that's called the post hoc test. And there are some familiar post hoc tests, but regardless, the post hoc test tells us way more specifically where the significant differences are. We said that if we accept the null, we simply just stop. We said computationally this is actually probably the most time-consuming of our analyses. But all in all, what we're really doing in this computation is performing what we call partitioning. And we're partitioning sums of squares. And we're actually partitioning that variation into between, within, and the total variation. This F statistic that we compute is just simply another ratio, mean square between divided by mean square within. So it's between over within. Between groups variation over within groups variation. We do this partitioning in the form of sums of squares, which we end up dividing by their respective degrees of freedom to give us a mean square, which we said is kind of a quasi-variance, something pretty similar to a variance, and we ultimately get the F statistic, and then we make our decision. We have a data set here with one factor. This factor A we called a grouping variable with three levels. In this case, we have three independent groups, so we have one factor A with three levels. We said if this was an experiment, this factor A would not only be a grouping variable, but it would also be the independent variable. And in this case, we would have three treatments. And we know that in any experiment, that group number one is the control group, right? Let's pretend this is an experiment. We have a data set here, 3, 1, 5, 0, 2, 0, 1, 1, 2, 9, 10, 15, 11, 12, 14, 15, 16, 14, 1, 0, 5, 2, 3, 6, 7, 8, 4. We have a mean of group 1 of 1.66. The mean of group 2 is 12.89. And the mean of group 3 is 4. And like I say a lot, whenever we get a data set, the first thing we do is look at it. And we see a mean difference here. And we wonder if this mean difference is real and significant, or if it just happened by chance. You know, one of the research questions we could ask, did the subjects in group 2, right, score significantly higher than the subjects in group 3 and group 1? I really don't know at this point. What I do know that our decision is going to be totally predicated on where our particular F statistic falls on that F sampling distribution. If F falls in that tail, our decision is going to be to reject the null. And one of our conclusions is going to be that that F is such a rare event, right, that it has been deemed a significant event. Pretty much same drill. If that F statistic falls somewhere in the middle, we're going to say that that event is not rare enough to be deemed significant. It's actually a pretty common event. We would accept the null and pretty much stop. We have a three-group one-way ANOVA. Therefore, we have a 3-group null, which states that we have no difference in the population between means, and a 3-group alternative. No difference, there is a difference. This particular problem calls for an O1 alpha. We know that before we run any statistical test, P equals alpha. We said that we have a couple different types of degrees of freedom in this one-way ANOVA. By the way, we have 3 groups, capital G equals 3, and 27 total subjects, capital N sub T equals 27. Degrees of freedom between is G minus 1. DFB is 2. DFW is capital N sub T minus G. 27 minus 3 is 24. We have 2 and 24 degrees of freedom. 2 between, 24 within. DF is 2 comma 24. We can find a critical value. We turn to page, I believe it's C24 in the back of our books. Was it C24? Yeah. Okay. We go across the top to 2, down the side to 24. We have a number there. What is that number? Right, 5.61. If f exceeds this, we have enough evidence to reject the null. This is telling us that at 2 and 24 degrees of freedom, about 1% of the area under this F sampling distribution falls to the right of this number, and about 99% of the area falls to the left of this number. And again, if f exceeds this number, we have enough evidence to reject the null. We said the goal of this computation, of course, is to reject the null. Sometimes we do, sometimes we don't. But procedurally, the goal is to fill in this ANOVA table. And it is within this ANOVA table where we identify the different sources of variation. And we do this partitioning activity in the form of sums of squares. Similar to Pearson R, we have to get the data set ready. We have to do a little bit of preliminary work before we actually start the partitioning activity. We have to do a sum x for each group, a sum x squared for each group, and then bring it into summation totals. In this case, sum x for the first group is 15. Sum x for the second group is 116. Sum x for the third group is 36. Now we do sum x squared for each group. And again, class, it's not 15 squared. No, I have to do that because students make that mistake. Sum x squared for group 1 would be 3 squared plus 1 squared plus 5 squared and so on and so forth. Sum x squared for group 1 is 45. Sum x squared for group 2 is 1544. Sum x squared for group 3 is 204. We bring everything to summation totals. Sum x total, sum x sub t, this plus this plus this is 167. This plus this plus this is 1793. And then we take this 167 quantity per these instructions and square it. 167 squared, 27889. And we're ready to go. Getting the data set ready to actually do the partitioning. The first partitioning step, sum of squares total. And if we look at this formula, we immediately see that it's a sum of squares. I mean, if you remember back from measures of dispersion, this is the numerator of the variance. If I were to go like this and put an n or an n minus 1, I would have a variance. Well, this isn't a variance, but it's a measure of variation called the sum of squares. we can now just fill in sum of squares total is the sum x squared sub t, 1793, minus the sum x sub t quantity squared, 27889, over the capital N sub t of 27. Sum of squares total, 1793 minus this quantity right here, which is 1032.92. Our sum of squares total in this case is 760.07. 760.07, we take this number, we put it where it belongs. SST 760.07. Great. We're on our way. Our next step in this partitioning activity, sum of squares between groups. And we said that this is a little bit bigger of a deal, but not that big of a deal. SSB, we open up a bracket. The sum x for the first group, 15 squared, over the n of 9, plus the sum x for the second group, 116 squared, over 9, plus the same for the third group, 36 squared, over 9, close the bracket, minus this quantity right here, which is actually this quantity right here, which we already computed to be 1032.92. So let's just write it in there. Now we have some, arithmetic busy work, and I actually did all that for you. This whole quantity turns out to be 1664.11. Minus our 1032.92. Sum of squares between groups is 631.19. And we take this number, we put it where it belongs. Sum of squares between 631.19. Great, we're actually almost home now. And if we remember, and if you look in chapter 12, between plus within equals total, right? Between plus within equals total. So given that, we can actually back ourselves into SSW. We can just simply say the sum of squares within groups is the sum of squares total, 760.07, minus our sum of squares between, 631.19. Sum of squares within groups, 128.89, or something pretty close. And we put that where it belongs. We've done a lot of arithmetic here, and we just kind of stop and take a deep breath. And we look at the table, and we finish. We do what the thing tells us to do. SS divided by DF equals MS. Okay? So this divided by this is 315.59. This divided by this, 5.37. We know the F statistic is just another ratio. In this case, mean square between 315.59 divided by mean square within, 5.37. F ends up being 58.77. F equals 58.77. Pretty large F statistic. Pretty rare event, right? Now we go through some formalities, just like we always have. We compare the calculated statistic to the critical value. We see it exceeds it. Therefore, our decision is to reject the null. Yeah. So as a result of that needle shift from 561 over to 58.77, we know that the p region got smaller, right? If p is less than alpha, we reject the null. We rejected the null. We have statistical significance. Now again, there's about a 1% chance that my decision to reject this null is not a correct one, so I rejected with about 99% certainty. If I were to replicate this 100 more times, theoretically I would reject the null correctly, right, 99 times, incorrectly reject it 1 time. The probability of a type 2 error we know is irrelevant. It's kind of like a non-issue. We've computed a significant omnibus F. Therefore, what is the next step? The post hoc test. You could choose from a number of them. We said that the 4 really popular ones are Tukey, Scheffé, Dunne, and Bonferroni. Look in any scientific journal that runs an ANOVA. Tons of articles, you will see one of these. Lately you see a lot of Bonferronis. Regardless, in this case, whatever post hoc you decide will compare the means of group 1 and 2, 1 and 3, and 2 and 3. And it will tell us more specifically where the significant differences are. In a typical research report, you might see, you know, asterisk here, NS, asterisk. Asterisk means a null hypothesis has been rejected. What this implies, we ran the post hocs. We have statistical significance at 0.1 alpha between the means of group 1 and 2. Non-significant difference between 1 and 3. Therefore, p would be greater than 0.01, correct? Significant difference between the means of group 2 and 3. This is just a typical report would most likely look like this. Why were we able to reject the null? We had enough power. Let's readdress that. The 4 elements of statistical power. Between groups variation, sample size, alpha, and within groups variation. Yes? Why were we able to reject the null? Well, let's take a look at it, those 4 elements. We don't have a real powerful alpha here. It takes a higher test statistic to reject here than it does at 0.5. So we don't have a whole lot of power going for us in the alpha piece. In terms of n, relatively speaking, these aren't really large sample sizes. So we don't have a whole lot of power here. But as it turns out, we had enough between groups variation combined with not a whole lot of within groups variation. It made F large enough to be deemed statistically significant. So what we're saying here, we had enough power to have significance. We had enough of this stuff combined to eke out, so to speak, statistical significance. The one-way analysis of variance. Okay, go to the example, the automotive engineers. Draw an ANOVA table very quickly on the back of the sheet, and I will get this thing set up. We're now going to get into story problem examples. This analysis is used very, very widely in all kinds of different disciplines. This particular example comes right out of automotive engineering. It's quality control research. Listen very carefully. A group of automotive engineers released the results of a comparison of 4 popular minivans and reported them in the following table in Consumer Reports. One of the features the researchers compared was the distance in feet required for the minivan to come to a complete stop when traveling at a speed of 60 miles an hour. So the dependent variable is braking distance. Here's the data. Can these engineers conclude at alpha 05 that there is a significant difference in braking distance among the 4 minivans? Give me a second to get this data. We have a 4-group One-Way-ANOVA design, 1 factor A with 4 levels. Group 1 is Nissan. Group 2 is Mercury. Group 3 is Dodge. Group 4 is VW. Nissan Quest, Mercury Villager, Dodge Caravan, VW Eurovan. Here's the numbers. 150, 152. This third number should be 151, not 154, by the way. This third number should be 151, 149, 153, 153, 150, 156, 151, 155, Dodge Caravan, 155, 150, 157, 158, 155. VW Eurovan, Group 4, 167, 164, 169, 162, 173. 4 independent groups. We have 4 independent groups. Let us assume we've utilized random selection. So the Nissan group was selected from a whole population of Nissan Quests. The Mercury was selected from a whole population of Mercuries. The Dodge was selected from a whole population, millions of Dodge Caravans, and so on for the VW. Let's look at the means. The mean for Group 1 is 151. Group 2's mean, 153. The mean for Group 3, 155. The mean for Group 4, 167. And we have 5 minivans in each group. So our n's are all 5 in this case. The numbers that we see, the dependent variable, braking distance. The dependent variable is braking distance. Let's inspect the data. Remember, this is a course in data analysis. The numbers are telling us something, or at least at this point, the numbers are suggesting something. These numbers are pretty similar, but look at this number. On the surface, apparently, it looks like it takes the VW Eurovan longer to come to a complete stop after traveling 60 miles an hour than the others, as compared to the others. One question we have here, one potential research question could be, does it take the VW Eurovan significantly longer, there's that word again, significantly longer to come to a complete stop as compared to the others? If we have a significant omnibus F, the answer to that question would be yes, but we would have to proceed further with post hoc tests to determine specifically where the significant differences are. Is there a significant difference in braking distance across the means of these 4 groups? I don't know. What I do know that it all depends on where that F falls on the F sampling distribution. Same drill. What I also know is that we have a 4-group design, therefore we have a 4-group null. So we just add one more population mean here. We have a 4-group null and a 4-group alternative. This thing calls for an 0.5 alpha. Pretty standard alpha. We know that before we run any statistical test, our p equals alpha, right? In this case, G is 4. We have 4 groups. Capital N sub t, the total number of subjects, 4 times 5 is 20. Degrees of freedom between groups we know to be G minus 1. 4 minus 1 is 3. Degrees of freedom within groups, capital N sub t minus G, 20 minus 4 is 16. We have 3 and 16 degrees of freedom. 3 between, 16 within. Our DF is 3 comma 16. We can find a critical value. We turn back to page C26. C26 is our alpha 05 page. We go across the top to 3, down the side to 16, and there's a number there, 3.24. We know that if f exceeds this critical value, we have enough evidence to reject the null. And again, this is also telling us that in this particular f sampling distribution with 3 and 16 degrees of freedom, about 5% of the area under it falls to the right of this number. About 95% of the area falls to the left of that number. We have to get the data set ready to compute this omnibus f, to actually begin the partitioning activities. We have to do a sum x for each of our groups. And a sum x squared for each of our groups. Simple summations. These numbers are going to get rather large because our numbers, our dV in feet, which by the way is ratio level data, right? Is also, numbers are rather large. Sum x for the first group is 755. Sum x for the second group, 765. The sum x for our third group, 775. Sum x for our fourth group, 835. Simple sum x. Sum x squared for each of the groups. So it would be 150 squared plus 152 squared. This computation can get, there's a lot of, the numbers are rather large. I did this really quickly. Sum x squared for the first group, 114,015. 114, 015. Sum x squared for the second group, 117,071. 117,071. Sum x for the third group, 120,163. 120,163. Sum x squared for the fourth group, 139,519. 139,519. Simple summations. And again, make sure you get this correct. A lot of keystrokes. do not rush through this computation. It's not a sprint. You have to get this perfect. You have to get these numbers perfect. Now we bring everything over to summation totals. We do a sum x total, a sum x squared total, and then we take this quantity sum x sub t and square that. Sum x sub t, this plus this plus this plus this gives us sum x sub t of 3130. Sum x squared total, just bringing it all over to totals. This plus this plus this plus this gives us 490768. And then we take this sum x sub t quantity, 3130, and square it. 3130 squared, 979,6900. Get the data set ready to actually do the partitioning activities. Now we're ready to go. Let the partitioning begin. And our first piece, sum of squares total. Sum x squared sub t minus the sum x sub t quantity squared over the capital N sub t, and now we just fill in the blanks. Sum of squares total is the sum x squared sub t, 490768, minus the sum x squared sub t, 979,6900. Over the capital N sub t of 20. And we bring this thing down. Sum of squares total, 490,768 minus this ratio right here, this quantity, which is 489,845. Sum of squares total, in this case, 923. 923, we take this number, we put it where it belongs. Sum of squares total, 923. Our next step, sum of squares between groups. Because we have a four-group one-way-ANOVA design, we have to expand this formula a little bit. We'll just add one more little group here, plus the sum x for the fourth group, quantity squared over the n for the fourth group, close the bracket, minus this quantity right here, sum x sub t quantity squared over the capital N sub t, sum of squares between groups variation. And so now we do a lot of filling in the blanks. A lot of busy work here. And again, all intro stat students have to do this. It's just kind of a rite of passage. Sum of squares between groups. Let's do it. Sum x for the first group, 755. Quantity squared over 5 plus the sum x for the second group, 765. Quantity squared over 5 plus the same for the third group, 775. Quantity squared over 5 plus the same for the fourth group, 835. Quantity squared over 5, close the bracket, minus this piece right here, which is actually this piece right here, which we already computed to be 489,845. So let's put that in there, save some time. 489,845. 845. Now we just have simple arithmetic. Sum of squares between, and again we would square all these numerators, add them up, divide by 5. This piece right here, if we do the arithmetic, is 490,620 minus our 489,845. Sum of squares between, in this case, 775. 775. We take this number, we put it where it belongs. Sum of squares between, 775. We're almost home. And knowing that between plus within equals total, and if we want to, we can make this 19. The book does that, I don't, whatever. SSW would simply be the total minus the between. Let's do that. Sum of squares within is the total sum of squares, 923, minus the between group sums of squares, 775. SSW is 148. The sum of squares within groups, 148. And it's at this point where we can actually just stop a little bit and take a little breath. And take a look at our chart. Now we've come a long way. A lot of arithmetic, a lot of stuff. And we, do what this thing tells us to do, right? SS divided by DF equals MS. And we're going to use that MSB and MSW to compute F real simply. This divided by this is 258.33. This divided by this is 9.25. And we know the F statistic is just another ratio. In this case, mean square between groups, 258.33, divided by the mean square within groups, 9.25. F in this case is 27.93. F is 27.93. And we know our next step is the decision. It's always a decision. We get our calculated test statistic and we make the decision using the rule, which is also the critical value approach in the book. We compare the calculated statistic to the critical value. We see it exceeds it. Therefore, our decision obviously is to reject the null. Yeah. Another pretty large F we have here. We know that as a result of that needle shift from the 3.24 out to the 27.93, our P region became smaller than alpha. We know if P is less than alpha, we reject the null. Class, let's go back to the question now. We have enough ammunition to be able to answer this question. Can these automotive engineers conclude at alpha 05 that there is a significant difference in braking distance among the 4 minivans? Yes. Yeah. Yep. But why? Well, this is why. This F statistic, it's a rare event. Fs of this magnitude don't happen every day. Something rather extraordinary is going on. This is a pretty rare event. We know rare events are significant events. So we have an overall indicator of significance here. But we don't know specifically where the significant differences are. So we have another step here, right? It's called the post hoc test. And it is within this post hoc test where we will determine specifically where the significant differences are. In this particular case, because we have 4 independent groups, the post hocs will be obviously a little bit bigger. We're going to look at group 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4. This particular post hoc will do 6 separate little 2-group analyses, whichever post hoc you pick, but it will conduct 6 separate little 2-group analyses. And so just hypothetically, I'm just, if we were to run these, you might see a research report that might look like this. NS, 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 asterisk, 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 notes P is less than 0.05. And what this is implying is that non-significant difference between 1 and 2, non-significant between 1 and 3, non-significant between 1 and 4, non-significant between 2 and 3, but we have a significant difference between 2 and 4, and we have a significant difference between 3 and 4. And we would have one, of course, between 1 and 4. This is telling us, of course, where the significant differences are. About a 5% chance that my decision to reject the null is not a correct one. So I've rejected with about 95% certainty, right? And the likelihood I've committed a type 2 error is a non-issue. So again, don't let this stuff, this is just a lot of stuff that we take in steps. Yes?
On those post hocs, is that like actually a test that we run, or is this?
You're not going to run that, no. No, just know that you would run that. Okay. If you reject the null. If we accept the null, what will we do? No. We would just stop. Yeah. So in this case, we rejected. So in this case, yeah, we would run post hocs. And I'm just grabbing these, this stuff out of thin air here, but typically that's what it would look like. And again, why were we able to reject this null? Well, you know what? We had enough power. Let's look at that again, the 4 elements of power. We have a pretty standard alpha. This is kind of like a vanilla alpha. This is the pepperoni pizza of alphas, In terms of power, we have relatively small sample sizes, so we don't have a lot of power going for us in terms of n, right? But as, again, as it turns out, we have enough between groups variation combined with not a whole lot of within groups variation to produce an F statistic that's statistically significant. So again, we have enough power to have significance. The one-way analysis of variance, looking for significant mean difference, across the means of 3 or more independent groups. In terms of this situation, now that the engineers have determined a statistically significant difference, now they can take action. It takes the VW Eurovan significantly longer to come to a complete stop after traveling 60 miles an hour. What might they need to do? Go back to the factory in Germany, to the braking production assembly stuff, make some adjustments. So this is an example of how ANOVA is utilized in, of course, the real world. It's all utilized in the real world of science. This particular case comes out of automotive engineering. Okay, we're going to begin the next class with another example of this. This is going to conclude this class's session on one-way analysis of variance. See you next time.